Math 1314, section IC1, spring 2022, Tyler Junior College, section 7.2, polynomial functions, video 4, zeros and x-intercepts, factored polynomials. As you can probably predict based on the previous two videos, there will be another one in this series about zeros and x-intercepts, but with unfactored polynomials. But we're going to tackle the easier case first, where our polynomial is already factored. In the previous videos, we learned what a polynomial function was, some characteristics of the graphs of polynomial functions, and how to determine the end behavior of the graph of a polynomial function. In this video, we will explore how to find the x-intercepts of a polynomial function's graph. Now, this is something we've already done. We will find the x-intercepts of a polynomial function's graph the same way we found the x-intercept of a quadratic function's graph by finding the zeros of f of x. The intercepts of the graph of f of x are found by finding the zeros of f of x. In other words, finding the solutions to f of x equal to 0. I want to pause here for a second and highlight some important things. The x-intercepts can be found by solving f of x equal to 0. And by the way, this isn't just for polynomial functions. This is for any function. If f of x is already factored, then it's really easy. We just use the zero product principle. And remember what that means. That means if a product is equal to 0, then at least one of the factors is 0. Or in variables, if AB equals 0, then A equals 0, or B equals 0, or both. And we've seen this before. We've seen it time and time again, most recently in the section about quadratic functions. But the first time we saw it was way back when we talked about quadratic equations. Do you remember when we were solving things like x squared minus 7x plus 12 is equal to 0? And although we could get out the quadratic formula, another strategy was to factor. This will factor into x minus 3 times x minus 4, because -3 and -4 add to give -7, but at the same time multiply to give positive 12. Well, when we got to this juncture, we set each factor equal to 0, and that essentially separated the x's from each other. And we got x equals 3 and x equals 4. X equals 3 and x equals 4. But that's all the zero product principle says. The zero product principle says if you have a multiplication problem equal to 0, which we did at this point, then you can set each half equal to 0, which is what we did right here. It's very powerful because it allows us to separate variables that are attached to each other and pretty much solve for them individually. For our first example, we'll find the x-intercepts of the graph of f of x, where f of x equals 2x times x minus 4 times x plus 3. Notice that this function is already factored. In other words, already written as a multiplication problem. It's 2x times x minus 4 times x plus 3. And to find the x-intercepts, we have to find the zeros of the function. So in other words, we have to solve f of x is equal to 0. Well, this is actually pretty easy because this is already factored. F of x equals 0 implies that 2x times x minus 4 times x plus 3 is equal to 0. And according to the zero product principle, the only way this multiplication problem can equal 0 is if it's one of its factors is 0. This polynomial has 3 factors. You could argue it has 4. By arguing that the 2 and the x that I just put in a box are individual factors. But we can also look at it as a single factor of 2x, followed by a factor of x minus 4, followed by a factor of x plus 3. And because this product is equal to 0, we can use the zero product principle that says all we have to do is put each factor equal to 0. Let's do it over here. All we have to do is put each factor equal to 0. So 2x is equal to 0. X minus 4 is equal to 0, and x plus 3 is equal to 0. That separates the x's from each other, and we can solve them individually. The first one we would solve by dividing both sides by 2. That would give us x equals 0. The second one we can solve by adding 4 to both sides. That would give us x equals 4. And the final one we can solve by subtracting 3 from both sides. That will give us x equals -3. So it wasn't too hard to find the zeros of the function, and so it won't be too hard to find the x-intercepts. Now you have to be real careful when you're doing your homework, because when they ask you for the x-intercepts, they may ask you for something like this, or because an x-intercept is a point on a graph, it should have an x and a y. What we saw for were x's. So what are their y's? Well, if you're an x-intercept, then you are on the x-axis, which means you did not move up or down any, which means your y is equal to 0. This also makes sense because in a function, the x is in the input and the y is the output. So solving f of x is equal to 0 is like setting y equal to 0. And then in each of these ordered pairs, we just have our x coordinates of 0, 4, and -3. Now, which one does the homework want? Well, it really just depends on how it asks you to format your answer. If it asks you to type your answer as ordered pairs, it's looking for the bottom 3 answers. If it just wants to know the x coordinate of the intercept, then the top box would be your answer. Now, are we correct? Well, sorry. Yes, we are. Need some caffeine. But let's verify it. Now, I'll admit that we are doing this manually to be able to sketch the graph of a function manually, but it's always nice to get some confirmation that what you think is true is true. So we're going to check with Desmos. We're going to graph this function, f of x equals 2x times x minus 4 times x plus 3, and see indeed if we do have those x-intercepts. All right, we're at desmos.com. And we are going to graph, what was it, 2x times x minus 3 times x plus 4. Let me double check. 2x, x minus 4x plus 3. 2x, x minus 4, x plus 3. Now, we can't see all of this graph because it goes above the screen on the left and below the screen on the right, but we're only really concerned with the x-intercepts. I'm going to zoom out until we see the top and the turning points on the graph. There they are. There's a peak, there's a valley, but we're just concerned with these x-intercepts. So let's zoom in on them. A little bit too much. All right, we have an x-intercept back here at -3, 0, an x-intercept at 0, 0, and an x-intercept at 4, 0, which should be what we got. -3, 0, and 4. -3, 0, and 4. All right, so not bad. Let's try another one. This is actually pretty easy, but there's a couple of things you need to be aware of. The first of which is, well, first off, this is g of x, not f of x. Find the x-intercepts of the graph of g of x. G of x is equal to 3 times x plus 2 times x minus 1 squared. Now, there's two structural differences about this polynomial function that's already factored and this one back here. Do you see the differences? In this one, the number in front doesn't have an x on it. In other words, this first factor is just 3, not something like 3x, or back here it was 2x. Secondly, notice that the second factor has an exponent on it, whereas over here it didn't. Will that make a difference? And what about that 3 in front? All right. We're going to do this the same way we did the other one. We're going to solve g of x is equal to 0. So let's put the function equal to 0. 3 times the quantity x plus 2 times the quantity x minus 1 all squared is equal to 0. Now, this is already factored, meaning that it's already a multiplication problem, and it's equal to 0, which means we can just set each factor equal to 0. The first factor is 3. And technically speaking, being a factor, we're supposed to set it equal to 0. I want to pause there for a second. Actually, let's set all the factors equal to 0 first. The 3 we set equal to 0. The x plus 2 we can set equal to 0. And the third factor, x minus 1, we can set it equal to 0. And you may be wondering, what about the square? Well, we'll worry about that in a minute. Two of these we can solve. We can solve the last one, we get x equals 1. We can solve the middle one, we get x equals -2. But why can't we solve the first one? Why can't we solve the first one for x? Because there is no x. So it's hard to solve for a variable that's not there. So what does this mean? Well, this means if the three factors in the problem, 3, x plus 2, and x minus 1, the first factor cannot make the multiplication problem equal to 0. Multiplying by 3 doesn't give you a 0. Multiplying by 0 gives you a 0. But since 3 is not equal to 0 and there's no x, what that means is we can pretty much ignore this factor. Another way of looking at it is going back to the original equation right here. If I divided both sides by 3, the 3 on the left would disappear, but on the right, 0 divided by 3 is still 0. So the 3 is essentially ignorable there because it's a factor without an x. Excuse me. All right. I'm not sure why that blue box is still there. Let's get rid of it. Okay. So the point I wanted to make here was if you are solving a factored polynomial equal to 0, like this one, and one of the factors is strictly numerical with no x's, like the 3, you can pretty much just ignore it because putting it equal to 0 doesn't even make sense. 3 is not equal to 0, and there's no x to solve for. So we just say that factor won't contribute to the product being 0. Now we do have two x-intercepts. The first x-intercept is -2, 0, and the other x-intercept is at 1, 0. The 0 is just part of being an x-intercept since you don't go up or down to stay on the x-axis. Now we're going to check this one in Desmos as well. 3 times x plus 2 times x minus 1 squared. We'll save this and turn it off. 3 times, I already forgot what it said. Come on. 3 times x plus 2 times x minus 1 squared. 3 times x plus 2 times x minus 1 squared. All right, looks like we captured most of the graph. Maybe zoom out a little bit to see where it turns, although that's not what we're looking for. There are two x-intercepts here. One of them is at the point -2, 0. The other one's at the point 1, 0. Isn't that what we just said? Yep, -2, 0 and 1, 0. So finding the x-intercepts is pretty easy. You could write them as x equals, you can write them as ordered pairs. But did you notice something about this graph's x-intercepts and this graph's x-intercepts? We'll go ahead and highlight them there. Not all x-intercepts act the same. I'm going to zoom in a hair. Here we go. Not all x-intercepts act the same. I'm looking at 5 x-intercepts, one here on the red graph, one here on the blue graph, one here on the red graph, one here on the blue graph, and one here on the red graph. But do you notice anything about the second blue one? Well, the graph comes down and touches the x-axis, so that is an x-intercept. But then it turns around and goes back up. By contrast, all the other x-intercepts go straight through, like the -3, 0 on the first one, starts low, goes high, crosses the x-axis. This -2 on the second function, x starts low, gets high, crosses 0 in the middle, x-intercept at -2, 0. But this x-intercept over here is a little bit different. The x-intercept at 1, 0, which came from the second function, because it doesn't cross over to the other side. It touches and turns around. So the question we're going to try to answer in the next series of videos, or the next video, I should say, is the following. Did you notice the x-intercepts in the last graph do not behave the same way? Notice that at x equals -2, the graph crossed the x-axis. This was in the last one we did. Notice at -2, it crosses the x-axis. But look over here at 1. It doesn't cross, does it? However, at x equals 1, the graph just touched the x-axis, then turned around. The behavior of x-intercepts, i.e. whether they cross the x-axis versus touch the x-axis, can be predicted from the function f of x if the function is factored. How? Well, that's what the next video is going to talk about.